Okay. Right. So we'll start off according to syllabus with mechanics. We have for you mechanics and hydromechanics, right? A large part of what I'm covering today will be in your H2 syllabus, right? So I will be going slightly quickly. You may find that it's slightly too fast, but it's okay. Trust me, I know what is in your H2 syllabus. I've been teaching for a long time. So I will try, where possible, to point out the more difficult areas. All right? But if any time you really feel like you need to stop me, please just raise your hand and stop me. Okay? Nope, 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 nope. Okay, so classical mechanics, right, is in this domain, right? If you want to look at an overview of all physics, physics deals with the very small to the very big. Classical mechanics deals just nicely, right, at where we are now, right, in our human space, and also at our human speed, right? So if you want to look at all the rest, relativity, which you'll learn later on from Mr. Wong, will be at the speed of light. Quantum mechanics, also from Mr. Wong, the smallest, right, at normal speed. There is relativistic quantum mechanics. If I just said university, that's where it is. Relativist cosmology and cosmological physics, they are both at university levels. Right? So physics is the understanding and making sense of things in the quickest time. We have a lot of, that's why we start off chapter 1 of your physics as, well, errors, uncertainties, estimations, right? So back of envelope calculations, right? All this talk about solar power, can it actually work, right? Have you ever wondered this question on your own, right? All this talk about solar power, can it actually work? So here we have question number 1, which is an estimation question, right? So how would you go about doing it if you don't actually have the answer yet, right? The answer I printed for you because too much time has been spent copying the answer. I want you rather to understand the reasoning behind it. So there we go. Singapore, if you don't already know, is around 30 kilometers top to bottom, 50 kilometers left to right. It's roughly in the shape of a diamond or rhombus. Right, so we can roughly calculate the total amount of energy in a day by this equation. So 1%, being 1% of Singapore being covered with solar panels, half base height to find the area of Singapore. 1 kilowatt per meter square is the energy of light that we have, and 6 hours per day, assuming only 6 hours of sunlight a day. Okay, this gives us how much energy? 50 million kilowatts per hour. Kilowatt hours, sorry. That's a lot of energy. How much energy do we use a day? Can I guess? No idea. Right. It's roughly 20 billion kilowatts. I mean, of course, these slides were done not in the recent years, so this may be an underestimation, but the order of magnitude is about the same. Right? So theoretically, if we cover Singapore with solar power, solar panels, we could achieve it. What are some of the considerations that are not included? How can we put holes into this estimation that we have? Sorry? Yeah, correct. Efficiency, right? Conversion, rate of conversion. Like we assume that all of the energy that falls onto Singapore is, or that 1% is captured completely. It's not true. Efficient solar panels, how efficient are they now? Any idea? China is one of the big producers, right? Highly sponsored and by the government in some sense. 50%, no, not so high. The newest, one of the recent technologies that they want to use completely transparent solar panels. They say that the efficiency is about 10%. So that, you know, if you have solar panel, it's always black and dark, right? So they can't use it for windows, right? So the newest is that they have transparent solar panels which can put on all windows. If all windows become solar panels, then there's a massive improvement in the area that we can capture. Right? But the normal ones, you can go and Google it, right? I don't think it's more than 50%. In fact, less than it. Yep, these are other things that we need to be sure. Storage, especially storage is a big problem and hence a big industry for technology. Right, next, done. Yay, kinematics. I've just covered measurements in like split second. Kinematics, you have covered that in your secondary school. You have started a lecture today. Right, also continuing lecture today with Mr. Quack. This is displacement, right? Between R2 and R1. Any questions? Should we look at this? No. Okay. Velocity is the rate of change of displacement. Instantaneous velocity, oops, this one should be white. Right, is the velocity at a certain time. So the direction of V is tangential to the path at a point in the direction of motion. So, any questions on that? Okay, have a bit fast, huh? So this is the general part. The real test comes in the application. Let's see if you can apply it. So next is acceleration. Acceleration is the rate of change of velocity. Da-da. And again, instantaneous acceleration is the one when time goes to zero, when time goes to close to zero. Right? Choose a very specific moment in time. There you go, you have the acceleration. Okay. Right. Not too difficult. If you talk about movement in 2D, right, then you have your x and y axis. You have your equations of motion v equals to u plus at. So here we have vx naught to represent the time at zero, which is the initial velocity. Everything else should be clear by itself. I'm assuming a high level of mathematics because you have got through the selection test. But if at any point you feel confused, you want more elaboration, you can stop me. But to tell you the truth, kinematics, this part is not that tough. Really, it's not that tough. Okay. So you see fanciful equations and symbols, and you're like, oh my god, it's so difficult. It's not really. It's really simple. It just looks difficult with the mathematics. So I and j are just unit vectors in those directions. Right? I is just a unit vector of the x direction. J is just a unit vector in the y direction. Right? So what you have here is that you just get the rate of change of the position of x over time in the I direction. That's essentially just the velocity of x in the I direction. Right? That's what it is. It's not that tough. Okay, and this is how the velocity changes with time. And hence you can use that to integrate it to find how the position of x changes with time. You realize you have x being the position, x not being the origin position, the change in the position being ut plus half at squared. Right? You've learned the equation. So these are just new ways to represent what you've already learned. Okay, summary. So the one you see on the left could be slightly less familiar, but it's essentially just a generalization of what you have on the right-hand side. Okay, and what you have on the right-hand side is just changed for both the vertical and horizontal axis. Okay, not a big problem. Projectile motion, yes, finally. Projectile motion you have learned today in your lecture? No, not yet. In kinematics. Interesting. Yesterday? Okay. So what happens is that when you throw a stone, it follows this arc, right? Yay. In projectile motion, we constantly assume that the horizontal component does not change. You can see here, right? I cannot use a laser pointer because I'm recording lecture, then your friends cannot see what I'm doing. You can see that the horizontal vector does not change over time. Right? It remains constant. And the vertical one changes due to the vertical acceleration. So when I throw a rock in air, the vertical acceleration stays the same throughout because the only force acting on that rock throughout the entire space is the wind. There's no other forces. If there's air resistance, what will change? What do you think? So you must then ask, okay, which direction does air resistance act? It acts in the direction against motion. So if it has horizontal velocity, there'll be horizontal retarding acceleration. So you see the horizontal arrow become shorter and shorter. And your vertical acceleration will oppose the velocity. So when it's going up, there will be downward force. When it's going down, there should be upward force. Okay. In addition to the weight. Alright, but this is just a simplified version. This is what you always use. You should know it. Do you know it? Yes, okay, very good. This is just the project. Well, using trigonometry to find the components vertically and horizontally. Velocity, well, there you have it. The horizontal component stays constant. The vertical component is just v naught y minus gt, where g is, well, gravitational field strength. Okay. Displacement is given as such, v naught x times t, and y is ut plus half a t squared. Easy, easy. Okay. So we generally decompose the initial velocity into two parts. Calculate whether it's the range or the height. Plug in the correct values, you can find the answers. Okay. So this is simple. Just a show of hands to see if you really belong to this group. Right? If you actually cheated on this. No, I'm joking. Which ball will fall to the table first? White ball. Blue ball. At the same time. Right. We have 3 out of whatever. So that's the majority. Right. So the white ball and the blue ball will actually hit the ground at the same time. I don't think you can see the blue one because of the light. Maybe can one of you just switch on one of the rows? Yeah, that would be you. Yeah, you have the closest displacement to it. Okay. But something more cool and actually more suited to your level of difficulty is this, right? Yep. The other one. No. Yes. Turn back on the first one. That's right. Thank you. All right. Zookeeper and monkey. So legend has it, right, that a hunter wants to hunt this monkey. So this is the hunter. In case you're thinking, this is the hunter. This is the monkey, right? So the hunter saw the monkey on a tree, and he decides to shoot the monkey. But this hunter did not learn physics, right? So he has a dart. If it's a bullet, it's more or less a straight line. He has a dart, right? Let's say he has a dart. A dart will have a projectile motion. It will curve. But he did not learn physics, so he aimed straight at the monkey. All right. So he shot. Boom. Monkey having instantaneous reflection because they are monkeys. He saw the hunter. He saw it with a long barrel. He didn't know it was a gun. But when he heard the boom, he realized it's a bullet, right? So at the point of time, he said, hey, he's aiming straight at me. I should move away from the line, right? Right? Because he's the monkey, right? So he said, oh, he's aiming straight at me, the bullet's coming at me, I should let go to move away from the bullet. But the monkey did not know about physics either. Because once he lets go, he falls at free fall, so does the bullet. Right? So the question is, will it do this, right? Will the bullet fly through the air and hit the monkey? Okay? So I've already given you the solutions, but just humor me a little bit. Don't look at the solutions. How would you prove this kind of question? Right? This would be a first level difficulty in the Olympiad question. Mathematically not trivial, but also not too challenging. This is the simplest, one of the simplest questions around. Right? So what happened at the end is that, the monkeys, both of them not knowing physics, allowed the hunter to hit the monkey. You notice that we have lots of examples with monkeys. I don't know why. Right? So first, you can show that the distance traveled by the dart is given by xt, right? And v naught cosine alpha, where alpha is the angle, times t gives you the horizontal distance traveled. Yv is the vertical displacement, right, by the dot. So that's not a problem. We have that. And that can be approximated into, can be rearranged, right, to show with your XD. So you form equation of YD and XD together. Now let's look at the monkey, right? What is the height of the monkey? With relation to time, you realize that you can form this equation, right? D being the distance away, D tangent alpha naught is essentially the initial height, right? Measured from the ground. Right? As time goes by, the second component, half gt squared, becomes bigger, so his height should get lower. Yes? So this is the initial height, D tangent alpha naught. This is the initial height. This is the component that adds, or rather reduces its height as time goes by, and it makes total sense. Okay? So you then compare the two, right? When xd equals d, yd equals ym. Right? Hence, the dart will hit the monkey. Questions? There are many ways to solve this. This is not the only way. This is just one of the ways. Okay? It's a classic problem. It's a classic problem in physics. Right. Ski jumper leaves a ski, moving in a horizontal direction with direction speed of 25 meters per second horizontally. The landing is at an incline 35 degrees below him. That means the slope is like that. Right? It's not the white color one. That's the background. That's the slope. Assuming there's a straight slope like that, where will he land? Right? Where will he land? This question again is tough. You probably will not find it ever in your own kinematics questions. Right? It would be a bit too tough for you in the normal H2, right? But in Olympiad, it needs to be expected. So mathematical ability is one of the key things, right? Creativity and rather persistence in the calculation. Right? So how would you try to solve this kind of question? Well, we try, right? We try to map out its horizontal direction in terms of time. We try to map out its vertical direction in terms of time. We try to remove the time component and see what we have, right? Let's try. Resolving, yeah, that's where we have x equals to d cosine 35 degree, right? Okay, and that will also be equals to 25 meters per second times time, right? So we let d be the length along the incline. Right, we then know that x, the horizontal distance traveled, is d cosine 35 degrees. Right, and that has to be 25 meters per second times time, where time is the total time of flight. Okay? Next, we say y. What is y? Y is negative d. Oh, interesting, negative d. Why do you put negative d? Because the displacement is downwards, right? And we usually take upwards to be positive. So negative d, sine 35, not a big problem, same idea as x. And the vertical displacement using s equals to ut plus half at squared. But now we take the vertical direction. Since the vertical velocity is 0, is half at squared. Here we use 9.8 because that's what the textbook use. But you should use 9.91 and 9.81, half at squared. You have these two equations. We want to remove t, right? We want to remove t from the equation because t is something that we don't know. So we rearrange, right? And we substitute t. Substitute t away. We get this mathematical scary looking monster, right? But it's actually not that hard. You look at the first equation. You let d cosine 35 degrees, you bring down 25 below it, you sub in this t, you square it, put it here. That's just what we did. Okay? Simplify. Ta-da! One equation, the only unknown is D. Solved. D is 109. So, few liners, you got it. So, a seemingly tough question with mathematics and enough skills in it, right, will allow you to actually solve it quite quickly. Okay? Questions? Okay? Right, this is the confidence building part of Olympiad. Because these are the easy ones. Okay. So, yes, don't worry about it. We'll take it slowly. I strongly believe that you're young, your mind is malleable. The more you do, the better you get. Don't worry about it. So there you go. With D, you can find the X and Y coordinates. The X direction travel and the Y direction travel. Okay? Oh, okay. Then we move on. All right, good. I like the confident knot. Right. In a detective story, a body is found 5.0 meters from the base of a building and beneath an open window 26 meters above. Would you have guessed the death to be accidental, and why? Why is there this question? Because it really was a real thing, right? It really was a real thing. In Singapore, we have a very famous coroner here. He's actually on the TV show now, Whispers of the Dead, if you actually have time to watch TV. Right? This was a real world situation. He saw that the girl was a certain distance in 2005, right? The girl was a certain distance from the ground, and he wanted to see if that's possible, right? Okay. So they did some simulation, right, of the real test, and the lawyer questioned him, right, on her test, and read this. So you're telling me that this is a simple physics that even an A-level student will know. This is not rocket science. Yes. Yes. And so there's one more. You should have 2 copies. Right, so it's actually a real thing. So let's look at it. You should have 1 question paper and 1 solution. The file, where's the file for attendance? This sign. This goes all into records. So, unfortunately. Okay. So let's look at it. This is the situation. Let's simplify with a diagram. Physics, we love to draw diagrams. 5 meters, that's the height. If you take gravitation and free fall, to be 9.81, you can calculate the time, or 9.80, you can actually calculate the time to be actually 2.3 seconds. Okay, 2.3 seconds. So if you only take 2.3 seconds to fall 26 meters, the question is, right, what must have been the horizontal speed? Right, what must have been the horizontal speed? That calculates easily A-level physics to be 2.2 meters per second. Now, if you are walking, what is your horizontal speed? If you are walking, your horizontal speed will be around 1 meters per second. If you are walking a little bit faster, it will be maybe up to 2.2 meters per second. Okay, please take one of each. Okay, there are 2 things here. Please sign your attendance. So, can it be accidental? If it was accidental, right, we will expect the horizontal velocity to be really close to 0. You can imagine, right? I'm not telling you to try it out. Don't try it out yourself. Please do not. You are Olympiad students. You are supposed to be quite smart. If you do slip and fall, your horizontal velocity actually will be very, 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 very close to 0. All right. So in fact, you should be hitting very close to the base of the building. Right. A normal walking speed is 4 kilometers per hour. It's still not fast enough. Right, so the horizontal velocity was actually double or almost double of this. So this allows us to make the assumption, or rather the guess, that it could not have been accidental. It is very likely that either the person jumped, right, with a certain speed, or someone threw him down or her down. Right? So it's not very likely. Any questions? Oh, range. Do we not have it here? We do not have. We'll discuss that later. No problem after the lesson. It's quite simple. I just need time to work it out for you. Okay. Right, here let's pause.